Hi there once again, and welcome back to this course in ENSC106. And right now we are going to start our new topic on torsional members. We are already done with members in axial loadings, right? Oh, say axial loading. It's a loading that's perpendicular to the cross-sectional area concerned. Right? And typical examples of actual members are columns, struts, some members of trusses, braces, um, and many more. And after this, we discussed members in direct shear. So example of that is connection or some bolted connections. And just note that it's not always it's not always the case that the bolted connection is in shear because sometimes it can be designed like, for example, maybe in tension. That the bolt is in tension rather than in shear, right? Anyway, this is the most common example for members in the red shear, and if we have this tension members, for example. And if you check the cross section right here, the bolt or the fastener is actually being sheared, right, at some plane. So depending upon the design, like we can have double shear or we can have single shear and other types of shear as well. And they are classified as direct shear, right? So just keep it at the back of your head that there is still another type of shear that we will discuss later on when dealing with flexural members. Okay, and right now, what we are going to discuss are members that are subjected to torsional loadings. And when we say torsional loadings, it's actually loading along the. Actually, it's a moment. It's something like a bending moment, but along the longitudinal axis. The axis of rotation is along the longitudinal axis. Right, so if we have this, let's say this is our x, this is our y, and this is z. So the axis of rotation is along this line, and it's not always z because that depends upon our coordinate systems, right? So just take note that this is um, that the axis of rotation is along the longitudinal axis, and the moment there is what we refer to as torque, right? So in this video we'll talk about the stresses, actually torsional stresses and strains, right? So just like what we did here, we talk about actual stress and we also talk about the actual strains. And right here it's more on our example, I guess, if I remember it correctly, it's more on the stresses, but there is also strains in members in the rec shear, right? So for the stress equation, um, the derivations of the equations for stresses and strains can be found in many strength of material books or mechanics of materials books. So right here, what I'm going to do is just to simply lay out the formula for the stresses and the strains without doing much. Um, without dealing much with derivations, because after all, what we need is or our equations wherein we can solve them. Wherein we can solve the problems given. Right. So for the shear stress, torsional shear stress, this is given by this formula equation T, and this is rho divided by J. Right. So here's our shear stress or torsional. This is our torsional shear stress. And if it's a stress, then that means that the unit is in pascals or psi, right? So that's force per unit area, right? So it says here that the torsional shear stress is just equal to the torque. This one is the torque, and the unit of torque is the same as the unit of moments. That's Newton meter. And this one is the radial distance, or sometimes if we talk about the maximum distance, yeah, we refer to that as radius. But it's actually I think a more precise or a more general term is this radial distance from the axis of rotation. And if it's a distance, then the unit is simply meters. And this one is the polar moment polar moment of inertia, and this is in meter to the fourth, so that's length, unit of length to the fourth. Okay, so just recall that this is I mean that this polar moment of inertia is the moment arm taken is the radial distance. So it has also a relationship to the moment of inertia, letter I, for the bending moments. Alright, so right here in our lecture handouts, alright, so here's our lecture handouts, and there is a figure here. Like, for example, we have a shaft, and this shaft at one end, this is fixed, and in the other end, we subject that to torsion. All right, so we have external loadings and we have this fixed support right here. So if we cut a section along the shaft, what we see is internal forces, right? So right here we have an internal force, and just take note that we are referring to this portion of the section, so that's why we have this direction. So right here, if this is the the torque or the internal force, then there's gonna be, or I mean, at an infinitesimal area, there's gonna be a force that's let's say if we consider this area, this is infinitesimal area, then there's gonna be a shear force that's acting on this infinitesimal area, right? So that's actually I mean, that's the reason why we call this a torsional shear. So it's a force that's parallel to the cross-sectional area, and it is observed that because this torque, this actually exists in all the section. I mean, in all the parts of the section, except that the distribution of these stresses, it is observed that at this, I mean, from the center or from the axis of rotation, it is 0, and it gets maximum, right? So it gets maximum to the outermost distance, right? So if you are referring to this distance, the radius, then you get a maximum you get a maximum shear right here, and you have a 0 shear at the axis of rotation. So it's actually true to I mean, if you rotate this, that's gonna be the behavior of the stresses. So we have a maximum shear stress at the outermost distance, and that outermost distance we refer to as the radius. All right, so going back to this equation, if we check this one, you would notice that this one is the internal force, and this radial distance, or the radius, because sometimes they use R, this radial distance in J, this is a geometric property. So again, you'll see that that the stress is just simply a function of this internal force and the geometric properties. Okay, so for the units, actually, if you check the units, you will get this pascals if you do some derivations on the units. All right, so now let's talk about the torsional torsional strains. By the way, for the sign convention, we have here the sign convention in our lecture handouts. And if this is our shaft and we cut a section at this portion, all right, so if we cut in this section, then we still follow the right hand rule, right? So if this is our right hand, so this thumb, this goes to the direction of the longitudinal axis, and this fingers right here, the four fingers, the that's gonna be the direction of the of the torque, right? So that's positive. Now if we consider this cut right here, so that means we consider this portion, then the following the right hand rule, then the positive one would be in this direction, right? So we have this direction because that's where the four fingers curl, and the thumb is pointing in this direction, in this longitudinal axis, right? So um, that's gonna be the um, sign convention, positive sign convention. Right, now let's move on to this torsional strain. Right, so for the torsional strain, now consider this shaft right here, and um, we're going to subject this shaft to some torque right here, and at this end, this is a fixed support. So if we consider this point, for example, initial point, right, initial point, and because of the torque, then of course there's going to be deformation, right? So from this initial point, let's say this is point one, and because of the torque, then it's gonna make it's going to deform, right? So that's gonna be the illustration if you view this way. Now if we check the side view, since this is fixed, then this is gonna be zero. So no matter how much torque you put in here, the displacement or the rotation of the point, at this fixed support, it's gonna be fixed, right? So this is gonna be the point right here, because this is a free end, right? So from this to that, that's gonna be the displacement. And the angle in between, from the angle produced from this line to this line, that's what we call the shear strain, right? So the shear strain is just simply the tangent of the shear strain is just the opposite divided by the hypotenuse, which is the length. Now, what is this distance? This distance is actually the arc length, right? So this is the arc length, and this is the L. And since this is sometimes we assume a small angle approximation, then that means that the tangent of the angle is just approximately the angle itself. So the shear strain is just S all over L. Right, so what is this S, this arc length? Now, this arc length, we can actually represent that in terms of the radius, right? This radius or rho, depending upon the points that, the point that we want to consider, whether the maximum point or some points right here in between. So this arc length is just simply the R times the angle, this angle right here. Right, so that's the R times the angle, right? And this is L, right? So we can also take some limit if you want. It's something like the limit of the change in this angle for the change in the length as delta L approaches to 0, right? So we can also do that, but the main goal right here is if we want to relate the force, I mean the shear stresses to the strains, then we need a relationship, and that relationship is actually the Hooke's law, generalized Hooke's law for shear, and it's given by this expression that the shear is directly proportional to the shear strain, and this proportionality constant is what we call the modulus of rigidity. Right, so if this is megapascals, if this is the stress and this is the strain, and the strain is it has no, I mean the strain is dimensionless, then this one would be also in terms of megapascals or gigapascals, right? So just take note, it's in pascals. It has the same unit as the stress, right? So recall that this shear stress is given by this equation, T times rho all over J, right? And this one, the shear strain, is given by the equation R times the angle of twist. This is what we call the angle of twist, R theta divided by the L, right? So if we substitute this to this equation, what we get is, right? Let's write it here. G times the shear strain, this is R, or let's just write rho to be consistent with this one, meaning that they are the same, right? Theta divided by L, right? So since we have the same rho right here, then what we get is TL all over JG, right? So here, this is going to be the relationship between deformation and forces, deformation and let's say stresses and geometric properties, right? So here's going to be our working equation for relating the deformation to the stresses. Now this equation, it has to be understood that it's an equation for this one, for homogeneous material, meaning it's only I mean the member, the torsional member is composed of one material only, like for example just steel or aluminum or whatever material, just composed of one material only, and it's for constant modulus of rigidity and uniform cross-sectional area, right? So that means uniform cross-sectional area all throughout the length, so there's no changes in the diameter, and also there's going to be a constant internal force. So that's going to be the equation. But if we have a condition like, for example, we have a composite material or compound axial, I think this should not be compound axial member, probably should be compound torsional member, and multiple loading points. So that means that let's say it's something like this. There's going to be changes in the cross-sectional area, and if you have loading points right here, then it's also possible to have some loading points right here, right? So or this one comprises of one material, like for example steel, and then the other one is aluminum. So if we have that kind of situation, then our working equation is just simply the summation of this um, these terms right here, the TL all over JG, right? So the torque at section 1, the length of section 1, the um, polar moment of inertia of section 1, and the modulus of rigidity of section 1, right? So we just have to add that up. Now if we have a variable cross section, like for example like this, so that means that there's not a definite cross sectional area uh, in some interval, but rather it's constantly changing. So that's why it says here variable cross section, variable g and variable j. So if that's going to be the case, then we are going to go for this integration, which is typical, right? So that's going to be the force deformation relationships. And the last thing that we will need is this geometry of deformation, right? So for example, if we have an indeterminate problems, and that means that we cannot solve it using equilibrium equations alone, then we need additional equations coming from the geometry of deformation, right? So for the geometry of deformation, it is possible that I mean, for some problems, there's gonna be this one is a coaxial torsion members. Then that means that this material right here. So I mean, this cross section is composed of two materials. So we have one material right here at the center, and another material um, at the outside, right? So let's say this is steel, and then this one is aluminum. So if they are going to be twisted together, so if we apply torques right here, then the deformation, if we check right here, the deformation of this material 1 would just be the same as the deformation in this material 2. Why? Because this deformation is just measured in terms of angle. Actually, it's radians, right? So that's gonna be, they are going to have the same deformation, right? So deformation 1 is equal to deformation number 2. And for problems that are connected end to end in series, so for example, here's our situation, and we have a fixed end right here and another fixed end this point, but we have let's say this is material 1 and then this is material 2. So the equations for the geometry of deformation would be this one, right? So you'll have the deformation of 1, okay, plus the deformation of 2. That's going to be equal to 0 or some constants if there are already gaps, right? So um, I guess I'll write it here, or it is also possible to have some constants right here if there are misfits or gaps or something. Okay, so I guess that's all that we need. So just to have a review of the equations that we need, which is very typical for structural materials. We need the stress equation, right? And this stress equation, we, we have this torsional shear stress. It's just T times rho, or sometimes I write R over J. And for the strain, or actually we'll just use deformation. Right here's going to be our work equation, TL over JG, and that depends because this one only works for constant cross-sectional area or prismatic cross-section and homogeneous materials, constant G. All right, and what else? We need the force deformation relationship. Right, so this force deformation relationship, actually, this must be the force deformation relationship TL all over JG. For the deformation, this is, I think shear strain is just equal um, to the arc length divided by the L, right? And we apply this, I mean, if we combine this using the Hooke's law, then what we get is this force deformation relationship, right? So we have, I mean, we need these three equations, right? And also the geometry of deformation. So depending upon upon our problems, then it's we can have something like this, deformation of 1 is equal to deformation at 2 if we have a coaxial torsion members, right? So we have a material right here, let's say one material and another material at the outside. So in terms of deformation, if we apply torque, then there's it's gonna be the same angle of deformation right here. But for situations like torsion members connected end to end in series, then we have this one is equal to 0, or sometimes is equal to constants if there are misfits, right? So what that means is something like this, right? So we have one material right here and then another material right here. They are connect, but there's going to be difference in the deformation. Why? It's simply because there's going to be difference in the modulus of rigidity. All right, so I guess that's all for our lecture, and in the next video we'll start our first sample problem.